Good afternoon, and welcome. My name is Siva Raghupati. Just a little bit of introduction about myself. I've been with Amazon Web Services for the last 6.5 years. I helped build a couple of services, Amazon DynamoDB, which is our NoSQL database store, and Amazon RDS, which is our relational database service. For the last 4 years, I've been working with customers, including Amazon.com, on building some of the big data, guiding them build some of the big data solutions on AWS. I'm here to share some of my experiences with you. Hopefully, you'll find that interesting. Thank you for being here. I'm delighted to be here as well. So I think you went through the keynote this morning. I think it was phenomenal. So I think I'm going to touch on some of those pieces or services that Andy introduced this morning as well to see where it fits into the big data ecosystem. My slides are already a little bit old. I'm missing a couple of pieces as well. So, in terms of what to expect from this session, we'll go through some of the big data challenges. I'll give you my perspective as an architect on what I'm seeing come in these days and what kind of problems I'm solving, are helping solve on behalf of customers. Then we'll also go through, I'll go through my view of how to simplify big data processing and what technologies to use, why, and how. And we'll also go through some reference architectures and design patterns towards the end of the presentation. So I'm not going to go through any code if you're looking to see code. I believe that you should get the architecture first and then start coding after. So I'm going to concentrate on architecture in this talk. Well, the way I see this is it's ever-increasing big data. The volume, velocity, and variety of data is ever-increasing. What that means to me on a daily basis today is customers are wanting to build systems that can handle millions of requests per second. Again, I repeat that, millions of requests per second and billions of events per day. About 4 years ago, somebody doing 150 or 200,000 requests per second was a little bit rare, and it happened. But today, a lot of the vendors who are actually, especially companies doing energy meters, et cetera, are testing things with 100 million requests per second. So that's becoming the norm these days. The interesting thing that I observe is that even though this is large workload and ingesting probably tens of terabytes of data per day, the time to build these systems have really shrunk. We're looking at maybe a handful of developers, in some cases one, building the system in about 3 to 4 weeks in a sprint. The cloud services that I'll go through has enabled this innovation possible. So it's no longer needed to, you no longer have to wait for weeks or months to build these systems. You can build them in weeks if you have the architecture right. So getting the architecture right is key for building systems fast, and that will scale to any throughput or any workload. And sort of the big data evolution, from my perspective, a lot of the workloads are moving from batch to real time, and some of the companies are moving from real time to predictions, right? For example, instead of actually, if you're building a billing system, rather than creating a monthly report or a weekly report, wouldn't it be nice to actually alert someone if your bill, if your thresholds are going to be breached? And interestingly enough, in addition to alerting also tells you after the fact, wouldn't it be nice to say you're on a trajectory that you may actually exceed your budget, right? So again, you can apply the semantics to pretty much anything that you build. So there are systems now, and for example, Amazon Machine Learning service enables you to do some predictions on fast-moving data as well as batch workloads. So how do you build predictions in addition to real-time into your data processing pipeline is getting pretty key. I have a couple of kids, 6 years old and 10 years old. They got pretty excited when they saw this slide. I've been drawing pictures for the last 1 month in preparation for this talk, but when they saw this slide, because what I did was I really destroyed the entire little city my son and daughter created to take those 3 pictures at the very bottom. And I was looking for a good contrast between the colors, and I really had to apologize to my son when he came back and found out from a football game that Dad has completely destroyed his Lego city. So when we showed this slide, hopefully I'll show this slide to him in YouTube, and it'll feel cool. So in essence, that's what is happening. In other words, we're putting like a head or intelligence into big data processing systems, and if you're familiar with Lego, there's a lot more to that picture, the toy on the right side. So we can do a lot more. So we're not alone. There's a plethora of tools to solve big data problems. On the left side, the Apache ecosystem is creating some amazing tools. I want to call this the zoo of technologies with the zookeeper, starting with the Hadoop, the elephant, Hive, Pig, Spark. Nowadays, if you go to any big data conference, Spark is the answer no matter what the question is. So I think looks like that's probably true. So we'll see how to use Spark. What are the pros and cons of Spark? How it fits into the big data ecosystem as well. I thought Spark was the answer, but turns out that squirrel at the very bottom on the left, which is pink. Anyone know what that is? It's called Apache Flink. I think that some people are raising their hands. Apparently, the squirrel is going to compete with Spark to see who does better. So the key point for me in this slide, before I get there, on the right side, right? Every time you come to reInvent, we gleefully announce, we're excited to announce a whole bunch of other services. For the next year, probably if I do the talk again, I don't know, maybe one slide. I need to have 2 slides there to fit more pieces into this. So the key point here is that when you build your architecture, it needs to be amenable for change. So in other words, if there is a new technology that's born, all of these new technologies are born to solve specific problems that we're seeing. How does it fit into your architecture? If you have to redo every single time, every 2 years, the landscape changes, right? So that's something that I've factored into some of the design patterns that I'm going to be suggesting in the course of the talk. And this is sort of the question that most people have when they call a solutions architect for help. Hey, is there a reference architecture? What tool should I use? How? And more importantly, why? We don't tend to visit why. In many cases, I think we should get started there in explaining why. Then the what and how kind of falls into place. I'm going to try to touch on some whys, which I have some visibility into this as I was building services, so I'm going to try to lay out in terms of why it makes sense to use specific technologies. So before I get started, I'm going to lay down some fundamental principles. These principles have been tried and tested for a long time, and they hold good. If these premises are wrong, then my architecture won't work. So, but I've seen this work for the last 4.5 or 5 years, so I'm pretty confident in this. First, I think when we think about big data pipelines or building big data pipelines, we should be building decoupled systems. So, in other words, if there is a producer and the consumer, both have to go in their own speed, doing whatever they have to do, and then putting a storage in between to decouple these systems allows both of them to go at their own speed, right? When you really look at a big data pipeline, it's typically, sort of that process repeats itself. We'll see how during the course of the talk. And you should be using the right tool for the job. And what that means is really, you do have various access patterns, and various tools give you different access patterns. Marrying the two, making the right match is pretty critical. And when we build services at AWS, we typically build them to do a few functions extremely well at the lowest cost. Typically what happens is when the cost goes off whack, it typically means that you're not using the right tool for the job. I'll go through an example as to how that shows up. Be ready for a quiz. So, and using Lambda architecture principles, I'm not talking about the product AWS Lambda. I'm talking about the Lambda architecture, which is about actually building batch systems, using batch systems, batch processing, as well as real-time processing, doing the balancing between throughput and latency, and answering your questions in terms of building batch views and real-time views, and compositing your answers from batch views and real-time views. This has been tried and tested across many, many, many installations. Literally, if you look at any kind of ad tech company serving, let's say, millions of requests per second, under the covers, their pipeline is really actually a Lambda architecture pipeline, compositing batch and real-time systems and serving these, workloads, massive workloads, if you will, both massive throughput and massive scale. And leveraging AWS services, I talked about customers building these systems in 3 weeks, a single developer building the system in about 3 weeks. How is that possible? I think that's possible because of managed services. When we use services such as Amazon DynamoDB for NoSQL or S3 or Kinesis, you don't have to deal with managing clusters, maintaining software, et cetera. Day one, you create your table or you create your stream, you put data into this, and you get data out of this. I mean, there goes probably around 6 months worth of work that you would have done managing and getting the cluster ready for building systems. Last but not the least, I firmly believe big data should not be equal to big cost. And that's a fundamental premise of some of the architecture patterns I'm going to lay out. So let's simplify big data processing. The more pipelines I build, more big data processing looks like this. It looks like a pipeline with data coming in one side and answers going out from the other side. And there's multiple stages in the pipeline. Typical stages are ingest or collect. I'm going to use these terms interchangeably. Store, and after that, it's process or analyze, and consume or visualize. Those are the typical stages. Again, depending upon what you do, these stages may be slightly different. And also what I see is the idea of store and process kind of fundamentally gets repeated itself. There is a cyclical process there, and this process happens many times around. And why does it happen many times around? To actually satisfy your time to answer. There's a whole idea of time to answer between the data coming in and you getting answers. And there's certain throughput that you expect these pipelines to operate at. And obviously, there's a bottom line, which is the cost. This needs to not break the bank, right? So that's essentially it. And so now let's get into each stage and figure out what's going on in each stage. And so in terms of data collection, whatever is your stack that is actually feeding the data, I see a few data patterns here. Typically, you're either dealing with transactional data, what I call as transactional data, which looks like you're talking to a database. The client, an application server talking to a database. You're doing probably tens or thousands or millions of reads and writes per second, right? Small data sets moving really fast, back and forth. And as you go down, then you have logging frameworks that send, log collection pieces that send larger amounts of data. This could be megabytes of data that are accumulated in machines and then uploaded to some endpoint. And most recently, we're seeing stream processing technologies, whereas rather than sending all these logs in one file, you just send individual records as the individual records are being born. For example, if somebody is if you're thinking about Amazon.com, as people are buying things on Amazon.com, we capture the clickstream rather than actually packaging this clickstream, each application server packaging this clickstream and sending this and uploading this. If you actually send the clicks, you can see things like, well, where did this person abandon the cart? What were they doing just before they abandoned the cart or buy the product? What was the kind of the process that was going on, or what was mentally going on, on your customer's mind as you're doing it? We can pretty much do all those guesses. So that's why a lot of workloads are moving from batch to real time. I also introduced a search data type. Search is getting pretty popular. The ELK stack, ELK, Elasticsearch, Logstash, and Kibana is very popular. In fact, we launched a service, managed service called Amazon Elasticsearch Service that is catered to handling search data. I should have added one more category called Snowball. So we introduced Snowball. So UPS would be the mechanism that moves the snowball. But probably next year I'll add Snowball over there, and then maybe right on top of or somewhere around S3. But even if you think about Snowball, the data is really going into the file system. In this case, it's going to be S3, right? So in terms of a store, let's go bottom up. If you're actually capturing streaming data, what type of store should you use? So these are some of the managed services available on AWS for actually dealing with streaming data. Amazon Kinesis, which is a managed service for dealing with stream storage and stream processing. And DynamoDB Streams, which was introduced recently, also can be used for stream processing. I'll kind of contrast these services as I go along. And SQS and SNS, Simple Queue Service, and SNS can also be used for managing streams, but we'll actually compare and contrast what kind of problems that they're supposed to solve. In terms of the unmanaged solutions, Apache Kafka is very, very popular. And let's contrast these technologies. So before we do that, why don't we explore why stream storage? Stream storage does a few functions. First, it decouples producers from consumers. In this case, I've represented producers. There's producers 1 through N, starting from red through violet on the left side. And the consumers, there's two applications, consumer 1 and consumer 2. So the reason for producers to write to a stream storage is the decoupling piece that they bring in, right? And then it also persists. So the stream storage gives you a persistent buffer where, let's assume we're dealing with sensors or IoT, Internet of Things gateways. Those sensors and gateways can pretty much hand off that hot potato to an intermediate storage tier and then move on, because oftentimes they don't have the necessary memory or a disk to actually accumulate these messages. So third, they collect multiple streams. You may have 1 million devices writing to an endpoint. And so the decoupled producers from consumers, so the producers can actually, all these million producers can really log their data into a stream or whatever construct. For example, Kafka calls it a topic, Kinesis calls it a stream, and DynamoDB calls it a table. These abstractions are the same. There are endpoints that all these producers write to. And when these producers write there, you have an option of specifying some piece of your data is the key. What does that do? We'll go over this in a moment. So basically, it produces, before we get there, another property that the stream storage allows you to do is it preserves client ordering. What that means is if the producer 1 is sending packets 1, 2, 3, and 4, the consumer is guaranteed to receive the packets 1, 2, 3, and 4 in the same sequence the producer sent it, and which is a pretty important property of the stream storage. And that's one of the primary reasons in some scenarios need stream storage. And the other piece is really streaming MapReduce. What that really means is if you're building an application that is going to answer a question that says, give me the top, what happened to, what is the sequence of packets that producer 1 sent, and give me the maximum, minimum, and the average value. Let's assume if the producer 1 is really sending pressure or temperature, you want to find out what the maximum temperature is or average temperature is. You want to write an application that computes these kind of things. So the frameworks that go along with these services allow you to do things like, finding out the max, min, average, or a 1-minute metric or a 10-minute metrics or whatever you wish. So that property is possible because all of these frameworks latch on a single thread to a specific partition or a shard, and that aspect is guaranteed. So that thread is guaranteed to get all the inputs produced by producer 1. And so such computations are possible. And then last but not the least, if you're an IT manager or a CIO, you want various teams to run independently. Let's assume clickstream data is coming into Amazon. We have multiple teams actually looking at the clickstream data. You want team 1 to take the clickstream data and process this and do whatever they want at their own speed, not wait on team 2 to actually write the code and then pass on the output to them. So in other words, you can have independent teams processing the data. Not only it's a technological advantage, it's also a time-to-market advantage. So you can build parallel applications that can process this data and simultaneously at their own speed and have their own time to market, if you will. So those are some of the advantages that stream storage provides. Now, what about queues and PubSub? Queues and PubSub also have the first 3 characteristics are the same in terms of decoupling producers and consumers and persistent buffer and having the ability to collect multiple streams. They are the same. But they don't have any client ordering, and there's no parallel consumption possible. And then unless there's one exception to that, which is if you use simple notification service, and if the subscribers are multiple queues, potentially the SNS can parallelize this into multiple queues. And also there's no notion of streaming MapReduce, because literally in most of the cases, these become decoupling mechanisms. So this question often comes up in my design reviews. I thought I'll just add just for comparison here. Now, what I've done in this slide is to actually put down all these technologies, and I've come up with a criteria for measuring these technologies. I thought I wanted to share this with you, so you can, when you evaluate these technologies, you can think on these dimensions. Maybe you can maybe add other dimensions to it, but these are the key dimensions in my opinion. For example, line 1 says which services are managed, yes or no. Whether ordering, does the specific service support ordering guarantee? In the case of Kinesis, DynamoDB streams, and Kafka, there's an ordering guarantee, whereas in the case of SQS and SNS, there's no ordering guarantee. And then the delivery. Let's assume you write to a stream or a table. When you read the data back, when you consume it, is the delivery at least once or exactly once, right? So what happens in normal circumstances, you get exactly once semantics. Under edge conditions, some of these technologies, can give the same piece of data twice. Suppose you're building a billing system. You don't want to bill your customer twice. So you may want to think of deduping When customers get double billed, they lose they lose confidence and trust in you. It's pretty important for you to think about these primitives so that you can make the right, you can build the right systems with the right guarantees. And in terms of the lifetime, when you put data into these systems, how long does the data stay before it goes away? So in the case of Kinesis, it's 7 days. And in the case of DynamoDB, it's 24 hours. And in the case of SQS and SNS, 14 days. And Kafka is configurable. For example, Netflix is doing a talk. They're using Kafka there. And then they have a couple of priorities of systems. There's some high priority systems where they keep the data for 24 hours. For lower priority systems, they keep it for 12 hours. So such configurations are possible in Kafka, for example. So in terms of the throughput, literally, all technologies you can scale to any level that you want. And then these are intended for big data consumption. There's no limits on how much of data that you can put into these systems. You literally have to scale the table or scale the stream by adding more shots, et cetera. But you can scale them to any level you want. In terms of the MapReduce, other than SQS and SNS, all allow you to do streaming MapReduce. So in terms of the record sizes, 1 megabyte is the maximum record size in the case of Kinesis, whereas it is 400 kilobytes for DynamoDB, and then it's 256 kilobytes for SQS, SNS, and it's configurable in Kafka. And in terms of the cost, that's a pretty important line. Typically when you are confronted with these kinds of decisions, it is good to actually go through an exercise of doing the cost. What I did in my case was, for example, you go to the page for Kinesis pricing, and typically they give a pricing example. You basically run the example through all of these scenarios, right? The example there is 100 puts per second, and each payload is, I think, 25 or 35K. If you actually take that data point and do the computation, you'll see that the Kinesis price is fairly low for that kind of a scenario. In the case of DynamoDB, it was higher because data doesn't go away in DynamoDB. It is a table storage mechanism plus a stream. So it's higher, but if you need that functionality, you want to use that technology. So in the case of SQS, it's slightly higher than Kinesis. And Kafka, I presume I could not compute the actual cost. It should be the same, but the challenge there is I don't know how to factor out the admin cost. How much of time that somebody spent to build these clusters, maintain these clusters that comes in. But in terms of the machine cost, it should be fairly low to rig up a Kafka cluster as well. And now moving into the next phase, which is the file storage. What file storage technology should you use for storing file data? And I think the overwhelming answer is Amazon S3. So why is Amazon S3 so important or critical for big data? So it basically decouples storage from processing. A lot of these big files were actually stored in HDFS before. So if you're using Flume or FluentD, chances are you may be writing to HDFS. The problem with that is actually you need to run a cluster. You need to keep a cluster alive all the time and keep it running and keep feeding it. Whereas if you write to S3, you don't have to actually have a cluster running. So you can literally shut down your cluster. If you have to do processing, you turn on a cluster, you process your data, you shut down the cluster, and then the data stays. It's designed for 11.9's durability, so there is very unlikely that you will ever lose anything that you put in S3. And it has unlimited objects. You can put any number of objects in S3. The aggregate bandwidth that S3 gives is, there's no limits on aggregate bandwidth. If you have multiple clients accessing S3, you can do any number of reads and writes per second. You need to be careful with naming the files properly so you don't get into any kind of hotkeys or partition scenarios. As long as you conform to that best practice, you can put as much of data and get as much of data out of S3, and then you don't have to have a cluster running. Also, when you're doing big data processing, the EC2 gives you the spot market. When you bid, you throw in a bid price that you can bid for instances. Typically, these bid prices or spot instances are 50% the cost of the regular on-demand instances. So if you're using S3 as your storage mechanism, for getting your job done, you can bid at half the price and get the instances. In some cases, customers bid more than the price because the actual price that they give them is half the price, so that they're guaranteed to get some of these machines. So I think such things are possible if you use S3. So my recommendation would be, use S3, and you need to really find a reason why that won't work before you use something else. And so we also recently introduced various tiered storage options. For example, standard, S3 standard, And we also introduced a new tiered storage option, which is infrequent access. So if you designate some object as infrequent, you get charged much less if you really infrequently use this. And you can actually set a policy in S3 that says, after 6 months, move all these objects with this prefix from one storage option to another storage option. It could be from standard to IA, standard IA, or it could be from standard to Glacier, for example. And so what about HDFS and Glacier? Typically, HDFS these days is used for storing, keeping intermediate files. If you have a batch processing job that has multiple stages, and if the output of one stage is keep being passed on to the second stage, many customers use HDFS for storing the intermediate files and then passing along. And then that's for dealing with your hot data. I think of this as a hot cache, for your pipeline, for your processing pipeline. And what about Amazon Glacier? Again, Glacier, in relation, with respect to the cost, S3 is 3 cents per gigabyte per month. Glacier is, 0.7 of a penny per gigabyte per month. And then, so it's significantly cheaper as well, even though Amazon S3 is really cheap. And so you can also, again, set a policy to move the data between the various tiers. And moving on to the next stage, which is the database storage. What kind of database storage technology should you use for storing search and database data? Well, this is an anti-pattern for the cloud. I love Swiss Army knives, so I figured I'll use that paradigm here. They're pretty cool. They have all the tools you need, and you can pretty much do anything you want. The only problem is if you need a big screwdriver for fixing something, you need to probably get a big Swiss Army knife. Now, one of this, about a few years ago when I got this picture from Amazon.com, it was about $800, and that price seems to be going up and up, right? So these things are cool, but if you need to scale one specific dimension, it's hard to do. For example, if you used DynamoDB for the same use case, if you're doing 1 million writes per second, if you're doing 10 reads per second, when you provision a table, you can simply say, I want to do 1 million writes per second and 10 reads per second. You pay for what you provision. Whereas if you use a relational database, you really have to get read capacity as part of the writes. You may not be able to slice and dice this and get just what you want. So this is the anti-pattern for the database tier. So what is the right pattern? So the right pattern would be thinking your database tier as comprising of SQL and NoSQL, and really complementing that with cache and search. There are amazing NoSQL and SQL technologies. I included, Cassandra, HBase, MongoDB, as well as, in the SQL, we have Amazon Aurora, which Andy talked about this morning, MySQL, Postgres, Oracle, and SQL Server. RDS runs all of these engines as well if you want to manage solution, or you can run this yourself on EC2 as well. And again, on the search, we have Amazon Elasticsearch Service and the Cloud Search Service. Now, often I get asked the question, like, you suggested this, and how do you keep all these things in sync, right? And now, this is one of the architecture that's kind of evolving. For example, you can use an Amazon DynamoDB stream and have a stream processing application using AWS Lambda service or a KCL service to actually capture the data. In this case, I'm assuming I'm storing actually the database data in a NoSQL, in this case, DynamoDB. And then I capture the stream data and apply those changes to my search engine as well as my caching engine. This way, your application can look in the cache if there's a cache miss, and then update the database, and the cache gets propagated from the update stream. This would be a predominant pattern that will come into being. I see already customers starting to do this pattern. I thought I would lay this out for you. And the key point here is that your search and the cache data are going to be a little bit stale, and the staleness is usually in the order of a few, maybe tenths of milliseconds, and that's usually okay for most applications. And then if it's not okay, some cases what people do is they actually check in both places to see if the document exists in their NoSQL store to move forward. And so again, how do you pick the right technology amongst all these 4 different pieces? It comes down to 4 dimensions for me: data structure, access pattern, and the database, and the data and access characteristics, and the cost. Those are the 4 criteria typically I use to pick the right storage choice. And I think the second point I want to emphasize a little bit, because in a way, after I look through all these building multiple big data systems, the one thing that I want to drive home is, storing the data in the form that you access it eventually is the secret behind, building big data systems. The moment you do that, most of your downstream problems are solved. You can look up, if you are doing a key lookup, as long as you can store this as a key value type, you can look it up any number of times. Whether it's million or 10, depends upon you provisioning the right throughput capacity on your backend system. That's very easily doable. So I'll leave you with that secret. But moving forward, so if your data access pattern is key value, potentially you could use caches or NoSQL. If it's a simple one-to-many or many-to-many relationship, you should use NoSQL. And if it's a cross-table, if you have cross-table joins and massive transactions, obviously SQL can do that. And if you have faceting and search, if you go to Amazon.com, on the left side, we show you, all these products Prime eligible, or these, by you can actually facet by, manufacturer, facet by, specific properties such as if this is Prime eligible or not. So if you want faceting and search, a search service is the obviously right choice. In terms of data structure, if you have a fixed schema, using SQL or NoSQL makes sense. JSON, these days, most NoSQL databases support JSON as a first-class data type. Clearly using NoSQL or search there makes a lot of sense. And then again, for key value, it's caches or NoSQL, right? This is, when I think about the access patterns and data, I often think about a temperature gauge. And in terms of hot data, warm data, and the cold data, right? So typically, these are some of the characteristics of the hot data. When you're dealing with, think of, data in your cache, data in an SSD, and data in a spinning disk, for example, corresponding to hot, warm, and cold data. Typically, the hot data, the data set size is small. You're doing a very large number of requests per second. The latencies that you demand of hot data is very low in the order of milliseconds, and so on. As you move towards the right, the data set sizes become bigger. The latencies, you can wait to get some data, from because the data sizes are bigger. And then the request rate tends to be lower, but the payload seems to be much bigger. And then the cost per gigabyte tends to go from, anywhere from dollars per gigabyte per month to, maybe tens of cents or per gigabyte per month to penny per gigabyte per month, for example. And then in terms of the mental map, this is sort of the mental map I carry around in my head. I try to, sometimes it's hard to actually draw a picture of what's in your head. So in this case, what I've done is really, on the left side, there's a data structure which is sort of going from high at the bottom to low at the top. And then there's various attributes of request rate, cost per gigabyte, latency, and data volume. And if you look at all these services, there's a little bit of an overlap between them, but each one of them has a center of excellence. Let's say if you're dealing with very hot data, if you're doing tens of thousands of requests per second, chances are, some kind of a cache or NoSQL would be the right choice. If you're doing searches, somewhere it's in the middle, you're dealing with really hot data sets with the latency characteristics of a few milliseconds or a second. Potentially, something like a SQL or a search or NoSQL may be the right thing to do. As you go towards the right, Glacier, if you put data in Glacier, when you ask it back, you'll get it back in about 3.5 hours. So that's cold storage, if you will, right? So to be more concrete, what I did in this slide is to actually pick specific services, and then I've associated all these various characteristics. I didn't put actual numbers because those tends to be varying, but actually I will walk through some of this. For example, if you're looking at average latency, if you're actually putting the data in elastic cache, the latency would be about a millisecond. For DynamoDB, it'll be again a single-digit millisecond, about 3 milliseconds for a put or a get. As you move into Aurora and or RDS or SQL and search, it may be from milliseconds to seconds. And again, if you put data in S3, maybe it's hundreds of milliseconds. 100 or 200 milliseconds for a gigabyte of data is sort of normal. And again, Glacier, it'll be probably hours to get the data back, right? So this is sort of the spectrum, of sort of hot data to cold data and what various technologies can do. I'm not going to go through each and every line here, but I want to leave this slide for you for a future reference. So when you're choosing between these technologies, it's sort of good to know which region you're in and then zero in on a specific technology for your use case. And this has been very helpful for a lot of our customers. And then I keep updating this slide every year. Again, this is not precise, and these things keep changing. But as a designer, it gives you a sense of what to look for and what kind of characteristics to look for in various services, if you will. And now, are you ready for a quiz? So, OK, this is an email that a developer at Amazon.com sent me. So the person is currently scoping out a project that will greatly increase the person's team's use of S3. The person says, hoping you could answer some questions. The current iteration of design calls for many small files, perhaps up to 1 billion during peak. The total size would be in the order of 1.5 terabytes per month. Typically, when I hear something like this, I fire up an Excel spreadsheet or some kind of a spreadsheet and start plugging the numbers in. When I plug the numbers in, this is the way it looks like. Well, the person is trying to do a request rate of 300 writes per second. The object size is about 2K. And then, totally per month, the person is going to store about 1.5 terabytes of data. In terms of the number of objects per month, it's going to be 777 million objects per month. This is a very tiny workload for big data, but it's an interesting example. So how many of you think that we should be using DynamoDB for this? And how many think S3? DynamoDB, raise your hands, please. OK, I count like maybe about 10. S3. Whoa, a lot more in S3. Well, one of you is going to lose, right? Is that OK? OK. There's this thing called Simple Monthly Calculator. How many of you have used this one? It's a pretty interesting tool. It's not perfect, but it's pretty cool. It helps me a lot as an architect. And if you plug in those numbers, it has various tabs for each services. And then if you take that thing and plug it into the DynamoDB page and S3, in this case, it turns out that DynamoDB is going to cost $644, whereas S3 is going to cost $3,932. Who said S3? Folks, I'm sorry. Somebody's pointing to their friend in the left side. I'm not sure how that's going to play out when they leave this room. So whenever I do a slide like this and showed it to the S3 product manager, the person was really upset. Right? You're not actually pitching my product in the favorable sense. So I figured I'll put a compensating scenario. What I did in this case was, scenario 2, I made up a scenario 2. I actually changed the object size to 32 kilobytes, right? Well, it turns out S3 is the winner in this case for that workload. You know why? Actually, if you look at the pricing details over there, it turns out the reason why the old price where Dynamo was the winner is along those lines. If you're on the right side, if you see, the put or the list request costed $3,888 in the case of S3. That's what actually threw this out of shape. That's what made Dynamo win in a way, because S3 is priced and built for dealing with large number of files, but a little lower frequency in terms of the number of writes per second for DynamoDB. DynamoDB is designed to handle small workloads super fast, right? It really allows small objects. You can do millions or zillions of writes per second. And zillion is not a number, but just a term. So, but then in the case of S3, it likes very large objects. You can do a few writes per second. That's the normal usage pattern. So when we build services, the pricing equation really works out to actually push you in the right direction. So having this tool, when I do design reviews, about 20 minutes into the thing, I pass, and I tell the customer, let's do a cost computation. Let's see if you're going in the right direction. Usually, it ends up in one or two ways. One, the customer gives 2 thumbs up and says, going. The second thing, they say, well, let's stop right here, right? Maybe I should redesign, or I should change my requirements. Either one of those happens. Both are good, actually, solutions, rather than finding out that something didn't work as you anticipated, or it broke the bank a little bit later on. So let's go into the process or analyze stage. So in the case of process or analyze, just a confession here, I copied literally from Wikipedia what analysis meant, because I wanted to validate what I was saying was right? So in a short sense, analysis really means you're shaping and slicing the data, making it, kind of building or creating answers from your data, shaping it, modeling it, cleansing it, et cetera. All those things are loosely called analysis. I didn't know whether to call this process or analyze, so I'm going to call this analyze from now on. But think process as well. So some of the examples are interactive SQL. If you have a large body of data of petabytes, if you want to run an interactive SQL, if you want to actually fire up some visualization dashboard against this and process that data, I'm going to call that interactive analytics kind of workload. And then obviously you have batch processing, real-time analytics, and machine learning as well as examples. So let's look at each one of these. In the case of interactive analytics, you're taking large amounts of data, warm or cold data, and you want the answers to come back in seconds. If somebody is slicing and dicing the data in front of the dashboard, you don't want them to wait for 5 minutes or half hour, right? This data has to come back in a few seconds. And so that's interactive analytics. Batch processing, we all have lived this, basically running your Hive job or a MapReduce job to actually, it runs for hours or days and comes back with a result. That's batch processing, daily, weekly, monthly reports are examples there. And real-time analytics, this is fairly new. It takes a small amount of hard data, and you ask questions like, is this a fraudulent transaction that's in flight? Or can you give me a 1-minute metric of this specific dimension? What is my latency for the last 1 minute? Give me the max, min, average, or the 99th percentile. So that's sort of the near real time. When I'm talking about real time here, I'm talking about business real time. Now, business real time in my mind is in the order of maybe 250 milliseconds to a second, something around there, right? For most of the customers, they have been doing bad jobs in about hours, right? Anywhere in the realm of a minute or so is reasonably close to real time for them, for various KPIs. So I just want to set that up. So then we go to predictions via machine learning. Machine learning gives computers the ability to learn without being actually programmed. So in other words, what you're trying to do is you're building a model, and you're using some training data to build the model. So later on, when you ask a question such as, is this a fraudulent transaction, yes or no? And then the system is able to give you an answer, yes or no. And that can happen in real time, or that can happen in a batch mode, right? And then, for example, if you look at Amazon Machine Learning Service, we support both classification and regression. So you can ask questions like, is this transaction fraud or not? If a customer is shopping your site, this is a new customer, you've never seen them before, you can ask the question what do you think, knowing all the characteristics of the customer I have fed in and built a model, is there a high probability that this customer is going to be a high value customer for me? And then what could be the lifetime value of this customer in terms of maybe dollars per month or dollars per year? Such questions can be answered by predictive analytics. There's another one which is called supervised learning, which is clustering. Let's assume in Amazon we have various kinds of shoes. If you want the system to automatically classify based on the picture, whether this is a sandal or whether this is a shoe, the machines can do this on your behalf if you have trained them with enough data. They can actually do this classification. There's various algorithms in, let's say, Spark ML and others that support these kinds of questions and answers. And so what are the analysis tools and frameworks that you can use? For machine learning, obviously, Mahout, Spark ML, or Amazon Machine Learning works fairly well. For interactive analytics, Amazon Redshift, Presto, Impala, and Spark work fairly well. For batch processing, again, you can use classic MapReduce, Hive, Pig, or Spark. And for stream processing, you could use Spark Streaming or AWS Lambda or KCL. And if you're doing batch analytics on streaming data, you can use EMR, Hive, and Pig. What I've done on the right side is really actually stack up the systems. So, for example, Presto, Impala, Spark, Hive, and Pig can be run on Amazon Elastic MapReduce. Amazon Elastic MapReduce is a managed service for running big data applications, such as Spark, Hive, Pig, et cetera, and Spark Streaming included. So that's sort of the technology stack for you to analyze. So, what stream processing technology should I use? Now, what I've done here is actually taken all the stream processing technologies and compared them side by side. I'm not going to go through each one of those, but those are some of the dimensions that you want to think about. In terms of the throughput, all of them can handle any amount of throughput, and whether they're batch or real time, if you're using the Hive handler for EMR, that's a batch analytics, batch processing mechanism. If you're in terms of manageability, in that dimension, for example, Spark Streaming can be run on top of Amazon Elastic MapReduce. Apache Storm, you really have to manage the entire cluster yourself. Whereas in the case of Kinesis client library, you can use EC2 and auto-scaling, or if you're writing a Beanstalk application, you can actually run your KCL application on top of Beanstalk, so it can automatically do the auto-scaling on your behalf and actually run the cluster across multiple availability zones as well. And Lambda is a fully managed service, so you don't have to do anything. Literally, you write your function, associate that Lambda function with Kinesis stream, and then the function gets triggered as your events come into the Kinesis stream. That's a fully managed service, but it's only applicable for Kinesis right now. It doesn't work with Kafka as far as I know. And the other piece, the important piece that some people miss is fault tolerance or multi-AZ. So for example, Spark streaming is single AZ because it is running on an EMR cluster. If for some reason, usually data centers are fairly reliable, AZs are reliable, but if you're building a distributed system, we ask you to build multi-AZ solutions. So it is a single AZ solution. If you're building this, you should be building multiple. If this is you need this to be fairly reliable, you should be running Spark streaming on more than one availability zone. For example, in the case of Storm, again, you can do it in one AZ or multiple AZ. This is, you have to actually rig up a cluster that runs on multiple availability zones. In the case of Kinesis client library, if you use auto-scaling, you can actually span multiple availability zones. But in the case of Lambda, it's automatically multi-AZ. Even if an availability zone goes down, the Lambda infrastructure will launch the underlying servers to still continue to process the stream, even when a single availability zone goes down. So it's a multi-AZ solution. And again, Amazon EMR-based Hive or Pig is going to be a single AZ solution. And the various language frameworks I've included there, I'm not going to go through all of them. But I think often customers miss the fault tolerance aspect of it. I wanted to highlight that in this presentation so that you would build a very reliable stack. In terms of data processing technologies, what data processing technology should you use? So in terms of the query latencies, Redshift stacks up very high because it's very easy to provision, very easy to manage, fairly easy to use. Again, the maximum data you can store theoretically is 1.6 petabyte. As Andy announced in his keynote this morning, NTT Docomo is already having 4 petabytes of data. So if you really want more than 1.6 petabytes of data you want to store in Redshift, you can tell us, and we can basically allow you to launch more nodes, more than 100 nodes, for example. And so the other key point I want to highlight here is that in terms of the native storage, Amazon Redshift has its own storage mechanism. It basically stores data on local disks, even though it keeps a copy of the data in S3 all the time, and it automatically backs up to S3. Whereas all the other technologies can work with files both in HDFS and S3. Impala did not have the S3 support. They recently added that. And Presto works with files in S3. In fact, a lot of the customers for very large workloads are actually leaving the data in S3 and running something like Presto to access the data, to run queries against this data. So in terms of SQL compatibility, again, Amazon Redshift is fully SQL, almost full native SQL compliant, ANSI compliant. So various other pieces have various levels of compliancy. So in terms of ETL, I'll just highlight this. There is a product called AWS Data Pipeline that allows you to actually run a cron-like semantic where you can actually wake up a process, actually run an EMR cluster every 15 minutes or so or more, and then take the data in S3 and process this and put this in another store. We also have amazing technologies from various partners. It's in our partner page, whether Attenuity or Informatica or Metallion or SnapLogic, Alteryx. There's a lot of partners that have amazing integration solutions as well. I've included that for completeness. So in terms of the consume layer, let's spend some time in the consume area. So in the case of consume, basically there's 2 types of consumers here. Business users are data scientists and developers. In the case of business users, using products such as Amazon QuickSight, which Andy demoed in the keynote, the product that we launched today. And various other partner solutions are Tableau, Looker, TIBCO, MicroStrategy, Kibana, et cetera. Or you can have your own libraries such as Flot or D3 that actually access the data both from your storage subsystem, analysis subsystems. And also these days, notebooks are very popular, such as IPython notebook. For example, you can launch a EMR cluster and install IPython notebook to actually have a notebook view, to do your slicing and dicing of the data and share the notebooks across data scientists, et cetera. And putting it all together, I'm going to leave this reference architecture with you, and I'm going to go through some of the design patterns fairly rapidly. And in terms of the design patterns, think of your data processing pipeline as a multi-staged pipeline with having storage decouple various processing tiers. And if you have various processing tiers, as soon as you decouple that, you could have multiple processing tiers read data from a storage tier such as Amazon Kinesis here and write to multiple stages. In this case, Amazon Kinesis S3 connector is reading data from Kinesis, and writing it to S3, whereas AWS Lambda is processing the data that you put in Kinesis and writing to DynamoDB. So decoupling these systems allows you to run multiple parallel processes for you to slice and dice the data in a way we want, in a way you want. And as soon as you, again, separate processing and storage, in this case, Hive is processing data both from Amazon DynamoDB through an external table and S3 and doing a join between the data in two stages. So this is the beauty of actually decoupling storage from compute. It allows you to do downstream computations such as these. And now putting two dimensions together, these colors can be a little bit overwhelming. I just wanted to still present the idea. That's why I left those colors. There's two dimensions here. When you're dealing with data stores, you're dealing with hot data or cold data. On the x-axis, hot to cold. On the y-axis, your data processing latency. When something has as you go from low to high, as let's say Hive takes much longer to process compared to, for example, Spark or Impala. So Hive has a higher processing latency. That's what I'm meaning here. So when you're building real-time systems, so that's your stack for building real-time systems. For example, putting your data in Kinesis or Kafka and DynamoDB and running Spark streaming or Apache Storm or AWS Lambda for processing the data would be a real-time stack. Or you could put data in DynamoDB and run native Dynamo queries as well as using KCL or AWS Lambda to process DynamoDB streams to do real-time processing. So if you're dealing with interactive analytics, typically data goes into DynamoDB or S3, or you can copy this over to HDFS as well, and you can run Redshift, copy the data over to Redshift, or run Spark, Impala, or Presto on the data you put in HDFS or S3, for doing interactive analytics. So in terms of the batch, as you put your data in various, data stores, you can run Hive on them to do batch analytics. So that's sort of a mental picture of how to think about these two dimensions and the various types of things you can do, processing you can do. Now let's actually assemble some concrete stacks here. This is sort of think of this as a design pattern for real-time analytics. You have producer putting the data in Kinesis, Kafka, or DynamoDB streams, and you have consumers consuming the data. And in this case, for example, you can have either KCL or AWS Lambda or Spark streaming or Apache Storm process the data that's in a stream and generate alerts and put the alerts in SNS and notify, send an SMS message, or you can actually activate a queue or call a Lambda function downstream to notify other downstream systems. Or in many cases, what happens is you have a key performance indicator for your company. For Amazon.com, for example, we have a graph that shows order inflow. Anytime there's a little bit of a dip, we actually cut a say 1, and then we have various teams looking at what may be happening because we sort of know what our key performance indicator and how typically the graph looks like. So for each company, there's a key performance indicator, and ideally you can build real-time systems to actually show you what the key performance indicator is real time. This is a typical architecture for do that, where you keep the state in an appropriate data store. And one thing I missed out here, just to go back a tiny bit, is you can also run real-time predictions when a transaction is happening. If this is a new customer you've never seen, you can also basically call Amazon Machine Learning Service to figure out whether this looks like a fraud and actually either do the alert or not do the alert as well. So this is how you would add real-time, you would learn predictions into your real-time processing pipeline. So here's an example of interactive and batch processing. On the top is interactive analytics. Again, putting the data in S3 is key. And then you can either run Redshift or EMR with Presto or Impala and Spark to do real-time analytics. And then you can also trigger a real-time prediction. So you can also look up, as you're processing data with this, you can run a UDF, you can write a UDF function, and to quickly look up Amazon Machine Learning to see if this is a fraudulent transaction or if you're doing some kinds of analytics, such as give me the lifetime value of a customer, et cetera. So in the case of batch, we've been doing this for a long time, putting data in S3 and running Hive, Pig, or Spark to process the data is the right pattern there. And Lambda architecture, as I talked about, is very popular in large, high-scale sites. And here is an idea for how to create a Lambda architecture. Put your data in Amazon Kinesis and build a batch layer. And the batch layer would comprise of an S3 connector. And the S3 connector will take the data from Kinesis and actually put that into S3. You can actually the best practice there is to compress the files as you put that in S3 and properly do a windowing function, wait for a few minutes, or where the size of the file is a specific size to actually write the file. This way you can write big files and don't have to pay the big price that we went through the cost pricing calculator. And then once the data is in S3, you can run various technologies to process the data and generate an answer. In the case of a speed layer, this is one way of actually building the speed layer. You can use AWS Lambda or Spark Streaming or Storm to do your speed layer. In many of these scenarios, what happens is when you build downstream applications, you also need a serving layer. Typically, the serving layer is your database layer, and which is typically NoSQL or SQL complemented by caches and searchers to serve any number of requests per second, millions of requests per second, for example, right? You really need a serving layer to serve those requests. And you can add machine learning into this by both the batch processing as well as the stream processing layer, consulting a machine learning stack to be able to do machine learning on both your batch analytics and real-time analytics. So in summary, building decoupled systems, if you're building a big data processing pipeline, building decoupled systems is fairly important. And using the right tool for the job is paramount. We've gone through some examples of what type of characteristics that you should look for in matching your access patterns to what the various technologies can provide. And we walked through Lambda architecture ideas. Your log is your database is our current thinking in big data. And then having an immutable append-only log in S3 is super critical. So in many of my design reviews, I ensure that one pipeline writes to S3 properly. And then thinking of your processing layer as a batch or stream processing layer is super critical as well. And then obviously use AWS managed services. There's no reason to reinvent the wheel unless you have a specific reason why these services won't actually cater to your needs. And last but not the least, be cost conscious. And thank you so much for your time. And that brings the end of my presentation. Thank you.